The year 1896 marks a peculiar moment in the historiography of science, a point of retrospective canonization for a word that had languished in profound intellectual isolation for decades. The republication of Amedeo Avogadro's 1811 paper, Essai d'une manière de déterminer les masses, relatives des molécules élémentaires des corps, by the Olympic Club, served as a formal acknowledgement of a foundational insight that chemistry had taken half a century to fully comprehend and embrace. The original essay, appearing in the Journal de Physique, de Chimie et d'Histoire Naturelle, was a work of serene logical power, a theoretical edifice built upon a daringly simple hypothesis. Its proposal offered a key to unlock the deepest structural secrets of matter, yet its very elegance and conceptual leap proved to be a barrier to its immediate acceptance. This analysis will undertake a rigorous, sequential evaluation of the internal claims, logical structure, and deductive consequences presented within Avogadro's original 1811 text. We will proceed through the paper's intellectual architecture, examining the foundations of his argument, the deployment of his central hypothesis, and the far-reaching conclusions he derived, all within the specific context of the evidence and reasoning he himself provided. The objective is to illuminate the profound coherence of his system on its own terms, assessing the strength of the chains of reasoning that connected observable gas phenomena to the invisible world of molecules and their constituent parts. Section 1. The foundational premise of volumetric ratios. Avogadro commences his essay with an immediate and complete acceptance of the experimental findings of Louis-Joseph Gay-Lussac. The work's opening paragraphs ground its entire subsequent argument in Gay-Lussac's law of combining volumes, which established that gases combine in simple, whole number ratios by volume. Avogadro's claim here is one of interpretation. He posits that these simple macroscopic ratios are a direct and reliable reflection of interactions at the microscopic level. He treats Gay-Lussac's empirical data as a given, a set of physical facts demanding a deeper theoretical explanation. The first proposition of the essay is therefore that a definitive connection exists between the volumes of combining gases and the relative number of molecules involved in the reaction. This move elevates Gay-Lussac's observations from a curious empirical rule to a fundamental principle of chemical mechanics. Avogadro's argument implies that the spatial properties of gases hold the secret to their composition. He asserts that the distances separating particles in the gaseous state are so great and are so dependent on uniform physical forces like temperature and pressure that the individual nature of the particles themselves becomes secondary in determining the volume they occupy. This physical reasoning underpins his conviction that volume is a proxy for quantity at the molecular level, a crucial first step in his deductive journey. Section 2. The eponymous hypothesis of equal volumes. The second major argumentative step in the essay is the formal presentation of its most famous and consequential claim, what is now known as Avogadro's hypothesis. He proposes that equal volumes of all gaseous substances, when subjected to the same conditions of temperature and pressure, contain an equal number of molecules. This is presented as a primary hypothesis, a foundational axiom from which a consistent system of chemical calculation can be derived. Avogadro supports this conjecture by appealing to the uniformity of physical laws. He reasons that since all gases expand and contract identically in response to changes in heat, as described by the laws of Gay-Lussac and Charles, it follows that the underlying particulate structure governing this behavior must be similarly uniform. The claim is that the physical constitution of a gas, its bulk properties, is governed by the number of its constituent particles, with their individual mass or chemical nature having a negligible effect on the volume. Evaluating this claim internally, its strength comes from its immense explanatory power, a quality Avogadro will demonstrate throughout the remainder of the paper. He provides little direct experimental proof for the hypothesis itself. Its validation is meant to be found in the coherence and consistency of the results it generates. It is a brilliant piece of abductive reasoning, an inference to the best possible explanation for the established laws of combining volumes. This section posits a universal physical principle that transcends chemical specificity, suggesting that at a certain level of abstraction, all gases behave identically in a numerical sense. Section 3. The crucial distinction between elementary and constituent molecules, perhaps the most conceptually sophisticated and vital claim in the entire essay, is the distinction Avogadro draws between two types of particles. He introduces the concepts of the molecule constituante and the molecule Elementar. In modern parlance, these correspond directly to the molecule and the atom, respectively. The molecule constituante is the smallest particle of a substance that can exist independently in the gaseous state and is responsible for the physical properties of that gas. The molecule Elementar is the smaller, fundamental particle of an element that makes up the constituent molecule. The internal claim is that the reacting particles in a chemical combination, the molecules constituantes, are themselves composite and can divide during a reaction. This was a radical departure from the prevailing atomic theory of John Dalton, which conceived of atoms as simple, indivisible units that were the fundamental particles of both elements and reaction. Avogadro's framework allowed for an oxygen molecule to be composed of two oxygen elementary molecules, or what we would call a diatomic oxygen molecule. This conceptual innovation was the key that resolved the paradoxes arising from combining Dalton's atoms with Gay-Lussac's volumes. For example, the observation that one volume of oxygen combines with 2 volumes of hydrogen to produce 2 volumes of water vapour was inexplicable under a strictly Daltonian model, as it would require the single oxygen atom to somehow be present in 2 resulting particles of water. Avogadro's claim that the oxygen molecule could split into 2 halves elegantly resolves this contradiction. This section of his argument represents a profound leap in structural chemical thought, proposing a hierarchical organization of matter where the particles of gases are themselves divisible entities. Section 4. The application of the hypothesis to water and other compounds. Having established his theoretical machinery, Avogadro proceeds to apply it with meticulous logic to specific, well-known chemical reactions. His analysis of the formation of water is the paradigm case for his entire system. He begins with the established fact 2 volumes of hydrogen gas combine with 1 volume of oxygen gas to yield 2 volumes of gaseous water. Applying his primary hypothesis, this means that for every 1 molecule of oxygen, 2 molecules of hydrogen react. This combination results in the formation of 2 molecules of water. For this arithmetic to be possible, he argues, the single original molecule of oxygen must have divided into 2 parts, with each part combining with 1 molecule of hydrogen. Therefore, he concludes, the molecule of water must be formed from half a molecule of oxygen and 1 whole molecule of hydrogen. A further logical step is required. To maintain the integrity of the resulting water molecules, he deduces that the hydrogen molecule itself must also be composed of 2 elementary molecules, or atoms. This is because if a water molecule is composed of 1 oxygen atom and 2 hydrogen atoms, and it was formed from a hydrogen molecule, that hydrogen molecule must have contributed 2 hydrogen atoms. His framework thus leads directly to the conclusion that both oxygen and hydrogen gases are diatomic. He extends this method to other reactions. For the formation of ammonia, for 1 volume of nitrogen and 3 volumes of hydrogen, he deduces that the nitrogen molecule is diatomic and the ammonia molecule is composed of 1 nitrogen atom and 3 hydrogen atoms. Each step in this section is a demonstration of the internal consistency and predictive power of his claims. The evidence he marshals is the empirical data of combining volumes, and his methodology is pure deductive logic flowing from his initial 2 hypotheses. The evaluation of this section reveals a system of thought that is remarkably robust and internally coherent, providing for the first time a clear and consistent stoichiometry for simple gaseous compounds. Section 5. Determination of relative molecular and atomic masses. The 5th stage of Avogadro's argument is the culmination of his work, as indicated by his essay's title. Here, He demonstrates how his system provides a manner of determining the relative masses of the elementary molecules. The claim is that by combining his hypothesis with density data for gases, one can establish a reliable scale of relative molecular weights. Since equal volumes contain equal numbers of molecules, the ratio of the densities of two gases at the same temperature and pressure must be equal to the ratio of the masses of their respective molecules. For instance, by observing that oxygen gas is approximately 15 times denser than hydrogen gas, he concludes that a molecule of oxygen is 15 times more massive than a molecule of hydrogen. This provides a direct, experimentally grounded method for determining relative molecular masses. His subsequent move is to connect this to the masses of the elementary molecules, or atoms. Having already deduced from volumetric data that both oxygen and hydrogen molecules are diatomic, the relative mass of their constituent atoms maintains the same ratio. An oxygen atom is therefore 15 times more massive than a hydrogen atom. He proceeds to apply this logic to a series of substances, including nitrogen, chlorine, and carbon. His analysis of carbon compounds is particularly insightful. From the composition of carbon monoxide and carbon dioxide, he deduces the relative weight of the carbon atom. This section represents a powerful synthesis of volumetric data, density measurements, and logical deduction. The internal claim is that this method provides a superior and more certain path to atomic weights than Dalton's rule of greatest simplicity, which was an arbitrary assumption. Avogadro's method, in contrast, was derived directly from a physical hypothesis that explained a wide range of empirical data. He effectively lays out a complete operational program for building the entire system of relative atomic and molecular weights from a few core principles, Section 6 extension to non-gaseous bodies, and the concept of affinity in the final part of his essay. Avogadro attempts to extend his molecular framework beyond the gaseous state to encompass liquids and solids. This portion of the work is necessarily more speculative, as the simple volumetric relationships that anchor his primary argument are absent in condensed phases. His central claim here is that the molecular constitution he has deduced for gases persists in other states of matter. He proposes that the relative number of molecules in a given compound remains fixed, and that one can use this information to understand properties like density and crystal structure. He introduces the concept of spacing, or the distance between molecules, as a key determining factor for the properties of solids. He even connects his molecular ideas to the concept of chemical affinity, suggesting that the attractive forces between molecules could be quantified and understood in relation to their masses and compositions. For instance, he posits that the number of molecules of one substance can combine with another is a measure of their mutual affinity. In evaluating this section, one observes a move from rigorous deduction to more analogical and theoretical reasoning. While his specific claims about solid structures were premature and lacked direct evidence, this section is significant for what it reveals about the scope of his ambition. He was striving for a unified theory of matter, one where the same molecular principles governed the behavior of substances in all their forms. He sought to create a conceptual bridge between the new chemistry of atoms and molecules and the older, more qualitative physics of attractions and affinities. This part of the essay demonstrates a desire to show the universal applicability of his system, even if the tools to verify these extensions were unavailable in 1811. It highlights the forward-looking nature of his thought, anticipating the development of solid-state physics and crystallography by many Section 7 The case of carbon and the establishment of a unitary mass scale. A more detailed examination of Avogadro's treatment of carbon reveals both the power and the subtle complexities of his method. After establishing the relative masses of gaseous elements, he turns his attention to carbon, an element whose gaseous state was inaccessible, but whose compounds, like carbon oxide, carbon monoxide, and carbonic acid carbon dioxide, were well-studied gases. He uses the known combining volumes and densities of these oxides to deduce the relative mass of the carbon atom. i.e. analysing the transition from carbon monoxide to carbon dioxide, which involves the addition of half a volume of oxygen for every volume of carbon monoxide, he deduces that a molecule of carbon dioxide contains twice as much oxygen as a molecule of carbon monoxide. Combining this with density calculates the amount of the carbon molecule Elementar relative to height. His calculation yields a value of approximately 11.36. The internal claim here is that his method can be applied indirectly to non-volatile elements through their gaseous compounds. This was a critical extension of his program, demonstrating its utility beyond simple elemental gases. Furthermore, Avogadro makes a deliberate choice to establish his entire scale of relative masses by setting the mass of a single molecule of hydrogen as the standard, with a value of 1. This was a methodological decision aimed at creating a clear, unitary system. He then populates a table with the relative masses of various molecules and their constituent elementary molecules based on this standard. This act of creating a comprehensive table based on a single, consistent logical framework was a monumental step. It presented a complete, internally consistent system of chemical arithmetic that could, in principle, replace the confusing and often contradictory values then in use. The evaluation of this section shows Avogadro as a systematic thinker, keen on building a practical and universally applicable tool for chemists. Derived entirely from his core hypothesis, Section 8, the understated rhetoric and the source of its obscurity, a final evaluation of the essay's internal characteristics must consider its rhetorical and stylistic presentation. The tone of the essay is remarkably understated and devoid of polemic. Avogadro presents his revolutionary ideas with the calm, dispassionate logic of a geometric proof. He refrains from directly attacking Dalton's model, instead framing his own work as a completion and clarification of existing knowledge, particularly the insights of Gay-Lussac. He presents his claims as necessary consequences flowing from the evidence. His intellectual humility, while admirable, may have contributed to the work's long neglect. The essay lacks the forceful advocacy or programmatic declarations that often accompany scientific revolutions. Furthermore, the crucial conceptual distinction between the molecule constituante and the molecule Elementar was a significant epistemological hurdle for his contemporaries. The chemical community was still grappling with the very existence of Dalton's single, indivisible atom. The proposal of a second, divisible type of particle added a layer of complexity that many found unnecessary or counterintuitive. The very elegance of his solution, the divisibility of the molecule, was perceived as a flaw by scientific culture wedded to the principle of ultimate, indivisible particles. The internal claims, however logically sound, required a conceptual flexibility that the chemistry of the early 19th century was unprepared to provide. The serene confidence of his prose and the subtlety of his core distinction created a work that was both profoundly correct and eminently ignorable. Its reception, or lack thereof, can be seen as a direct consequence of this mismatch between its own sophisticated internal logic and the prevailing intellectual frameworks of its time. It was a perfect key for a lock that chemists were yet to realize they needed to open. In conclusion, Amedeo Avogadro's 1811 essay represents a masterclass in scientific reasoning, a work of extraordinary internal coherence and predictive power. Its central claims, hypothesis of equal volumes, and the crucial distinction between the molecule and the atom formed the pillars of a complete and logical system for understanding chemical composition and determining relative atomic masses. From the foundational acceptance of Gay-Lussac's volumetric laws, Avogadro constructed a deductive chain that led, step by step, to a unified and quantitative picture of the submicroscopic world. The section-by-section evaluation of his arguments reveals an intellect capable of holding empirical data and theoretical conjecture in perfect balance, using one to illuminate the other, while his more speculative extensions into condensed matter were less robust. His core program for gaseous reactions was flawless on its own terms. The long period of obscurity, that followed the essay's publication speaks volumes about the scientific paradigms of the era, which lacked the conceptual framework to appreciate its genius. The ultimate validation of his claims, championed by Stanislaw Canizaro at the 1860 Karlsruhe Congress, was a posthumous triumph for the essay's quiet, persistent logic. The 1896 republication was not the resurrection of a flawed idea, but the formal placement of a finally understood masterpiece into the permanent canon of scientific thought, recognizing that the internal consistency of Avogadro had so carefully crafted 811 was, in fact, the true reflection of chemical reality.